Good afternoon, everybody. So let me start our PhD defense by Biltu Mahato, multifunctional interleaves for composite laminate. The supervisors are Professor Sergey Baimov and Professor Stepan Lomov. So first of all, let me introduce the jury members and introduce supervisor. Can you switch the slide? I don't know. Huh? Yeah, so first of all, let me introduce myself. So my name is Albert Nasibulin. I'm a professor at the Center for Photonics and Engineering of Skolkovo Institute of Science and Technology. So until December 2022, I was an adjunct professor at the Department of Applied Physics and Department of Chemistry and Material Science at Aalto University. So I got my PhD in physical chemistry at Kemerovo State University and Doctor of Science at St. Petersburg Technical State University. So my main specialization is aerosol science of nanomaterials and their applications. So I'm a co-founder of 4 companies, so with like 400 papers and so on. Yeah. So the next jury member is Professor Amit Raval from the Department of Textile and Fiber Engineering of Indian Institute of Technology in Delhi in India. So he's a recipient of several fellowships like Alexander von Humboldt Research Fellowship, Fulbright, yeah, and many others. So he obtained his PhD in technical textile from the University of Bolton, UK. He also received a Master's of Philosophy from University of Manchester. So he has several years of postdoctoral research experience in various countries, including South Africa, Belgium, and United Kingdom. So his main specialization in non-woven materials, braided and double helix structures. So his research interests are the structure and mechanics of textiles, structure properties, relationships of carbon nanotube sponges, electrospun mats, low surface energy, yeah, and many others. So he has a successful background in academic research with more than 100 peer-reviewed scientific papers. His H index is 30. So the next jury member is Dmitry Kolominsky. So he is an assistant professor at the Center of Materials Technologies of Skolkovo Institute of Science and Technology. He's specialist in fluid mechanics. So he got his PhD from the University of Aix-Marseille from France. So he was a postdoctoral fellow in France, in Canada, in Japan. So his research concerns mainly with computational fluid dynamics and fluid-solid interactions. He has been involved in interdisciplinary international cooperative projects with biologists, with engineers, with different kinds of scientists. So his research at Skoltech is focused on computational fluid dynamics, application to the development of new design and manufacturing processes. He has successful background in academic research with more than 100 peer-reviewed papers. So he has H index is 22. So next jury member is Professor Dmitry Krasnikov from the Center of Photonic Science and Engineering of Skolkovo Science Institute of Science and Technology. So he received his PhD from Novosibirsk State University. So he was a researcher at Boreskov Institute of Catalysis, Laboratory of Nanostructured Carbon Materials, and postdoctoral fellow at Skoltech. So his research interest lies in physical chemistry, catalysis, nanotechnology, composites, and carbon materials. At Skoltech, he has been involved in research and on the formation of nanocarbon for energy transitions, synthesis of single-walled carbon nanotubes, graphene, and many other materials with a CVD method. So he has a successful background in academic research with more than 100 publications. So his Hirsch is 23. So next dream member is Quang Liu, so who is associate professor in the College of Aerospace Engineering at the Nanyang University of Aeronautics and Astronautics. So he received his PhD in engineering mechanics from the School of Aeronautic Science and Engineering in Beihang University in China. He was also a research associate at the School of Mechanical, Electrical, and Manufacturing Engineering in Loughborough University and postdoctoral fellow in Belgium. So his research mainly focuses on modeling of mechanical behavior of light weight materials, metallic materials, and porous media. So currently he is working on bio-inspired design of novel lightweight composite based on optimization tools, and he has optimization tools. So he has a successful background in academic research with more than 45 peer-reviewed papers. His Hirsch is 20. Yes, that's it. So now let me introduce supervisors. So Professor Sergey Abaimov, so he's a leading scientist, leading research scientist at the Center of Petroleum Science and Engineering of Skolkovo Institute of Science and Technology. He received his PhD from the University of California in USA, so having specialized on complex systems and applicability of statistical physics to damage phenomena. So in the fall 2009, so he was invited by Penn State University in Pennsylvania. So in 2010, Professor Sergey Abaimov joined Moscow Institute of Physics and Technology as an assistant professor in theoretical physics. So his research interest lies in the fundamental applied research in theoretical, computational, and experimental micro and nanomechanics. At Skoltech, his research focuses on nanocomposites, composite materials, micromechanics, and statistical physics. So he has a successful background in academic research with more than 100 publications, and his Hirsch is 17. So the co-supervisor is Emeritus Professor Stepan Lomov from Belgium, who received his PhD and doctoral science from St. Petersburg State University of Technology and Design. Since 1999, he worked in KU Leuven in Belgium, Department of Material Engineering, coordinated the Composite Materials Group. So from 2013 to 2020, and since 2020, so he's emeritus professor and in a collaboration work with Skoltech. So his research focuses on composites, textile science, and engineering, internal structure manufacturing, in-service mechanical behavior, nanocomposites, experimental damage mechanics, micro, meso, and nano-level geometrical and mechanical modeling. So he has a successful background in academic research with more than 1,000 peer-reviewed scientific publications. And his Hirsch index is 73. And then finally, so we are coming to the candidate, Biltu Mahato, who is a candidate in mechanics, mathematics and mechanics program at the Skolkovo Institute of Science and Technology, who got his bachelor in 2016 in aeronautical engineering from BTU, India, and Master of Science in 2019 in advanced manufacturing technologies from Skoltech. So he has a track record of academic excellence and scholarship. He has a practical experience working in industry and several internships. So his PhD research has given fundamental ground for the Skoltech Translation Research and Innovation Program grant. So his research focuses on the experimental and computational mechanics of polymer composites, nanocomposites, and carbon-based multifunctional materials for sensorial applications. So he has a very early research career with more than 15 reviewed scientific publications with an Hirsch index of 4. Now, so the floor is yours, so you have time to present us your dissertation.
Thank you, Professor Nasibul. Sure. Yes. Thank you, Elena. Hello, everyone. My name is Biltu Mahato. I am a PhD candidate in Mathematics and Mechanics program at Skoltech, and today I want to present my research result for my PhD degree at Skoltech. The topic of my PhD thesis is multifunctional interleaves for composite laminates. Composite laminates are widely used in various applications where high strength and high stiffness are desired for low weight, where the primary functional of the composite laminate is load bearing. However, now there are several new research directions in this polymer composite material where the idea of secondary functionality, adding secondary functionality to the FRP composite laminates is very demanding. This secondary functionality could depends on the requirements, and it could be from damage monitoring to structural health monitoring to several other applications. These material with more than one functionalities are called multifunctional materials. And such multifunctionality can be achieved by modification of constituents, either fiber or matrix or interface, by introduction of nanofillers. Here I show you one examples where this FRP laminates is modified for impact susceptibility applications using some nanofillers like graphene and some thermoplastic polymer. So these nanofillers could be anything, but carbon-based nanofillers are really popular. One of the popular one because of the high specific area and high mechanical and functional properties. Also, it comes in very diverse form, starting from 0-dimensional to 1D to 2D and 3-dimensional material. Among these vast choice of material, 1-dimensional material like carbon nanotube and in 2-dimensional material like graphene are very popular one. So for multifunctional material, there are several challenges, and one of the key challenges that was identified in this paper by Kinlos that was published in Science in 2018 was dispersion problem. So the problem here is that when you introduce these nanofillers in the FRP laminates, because of its high surface energy, it agglomerates, and this creates a very big problem. And because it creates stress concentration and so on and so forth, so several problems. So the dispersion was identified as one of the key problems for multifunctional composites. So to address this problem, the idea of master batch came in. And what is a master batch? Master batch is just a concentrated form of nanofiller mixed with some base matrix that will be suitable for our FRP laminates. Compared to the dry form, this master batch offers several advantages. For example, dispersing dry form of nanofillers could be technically challenging. So master batch is produced at industrial scale in industries with expensive equipments like 3-roll milling, which gives high quality dispersion of nanofillers. And because of these dispersions, the uniformity and consistency of nanofillers in the matrix can be maintained. Similarly, compared to mixing in the lab, it's a low cost because it's already performed by big machines at large scale in industry. So it gives the advantage of low cost. Similarly, handling nanofillers like carbon nanotube and graphene, it is from the perspective of health is very controversial because there are literature on both sides saying it's it has some health-related effects, and also from the side that says it has no health-related effects. So it's better to be safe than to be sorry. So using master batch gives us advantage in a way that it is not in dry forms, it's already mixed. So health-related issues is kind of solved to a level. Given this background, in my research, I try to understand three functionalities, namely hierarchical toughening, self-diagnostic capability, and cure status monitoring functionality. For these three functionality, I started with my research with electro-response polymeric veil, and then I had some results here and some negative results. Then I switched to another kind of multifunctional material. It's called epoxy CNT nanocomposite interleaf. So starting with electro-response polymeric veil. In FRP laminate composites have very good in-plane properties, but these FRP laminates suffer from poor out-of-plane properties. Because of these poor out-of-plane properties, it could fail by damage like delamination. Delamination could come from several kinds of loads. For example, design loads, it could be either external or internal ply drops, or transition between solid and sandwich structures. Similarly, in the design of composites, also it could come from beam corners or places where beam interacts with the skin, or it could just come from curves, straight free edges or curve free edges. These are the design conditions which could give rise to delamination. Similarly, delamination could also come from just a simple impact. In impact, it could be fiber breakage or some internal damage. Fiber breakage are visible damage and it can be repaired. However, the internal damages are barely visible, and these could be this could cause a catastrophic damage. Because when these damages are there, it causes loss of mechanical property and it leads to catastrophic failures. Along with this delamination could also come from just environmental factor like high temperature or some hygroscopic conditions, or sometimes also it could come from mechanical defects, manufacturing and mechanical defects. So to address the problem of delamination, there are several methods. Here I list, I start with micro-scale modification method. In micro-scale modification method, there are several types, starting with 3D weaving, stitching, Z-pinning, fiber hybridization, and short fiber interlaminar region. These methods improves fracture toughness and solves delamination to a level, but these methods come with a problem like resin pockets, or could cause loss in the in-plane mechanical properties, and also self-diagnostic is not possible. Along with these micro-scale modification, there is another modification called interleaving polymeric veil. These veils are produced from thermoplastic material, which is insulative, so doesn't give self-diagnostic capability. But introducing such veil solve the problem of resin pockets, and it doesn't change the in-plane properties, and also improves fracture toughness. So once we go in this direction, the several research questions comes up. For example, these are produced by electrospinning, but then how popular is this technology for composite laminate? Similarly, there are several thermoplastic polymers. Which one would we use? What one would we choose? And it improves fracture toughness, but what are the toughening mechanism? It could be another research question, and similarly about the diagnostic capabilities. So here are some of the results for this method. This method is really popular. First, this technology was patented in 1999 and published in 2000. So if you see the literature of fracture toughness, this method of improving fracture toughness contributes about 6% of the total published papers. So we can say this technology is in growth phase of the technology growth curve. Similarly, when the question is about which materials, so it can be answered in two ways based on material choice. So here 5 materials were selected as the most popular one that are used for this application. Also, it can be seen from these two plots. Depending on the requirement of fracture toughness improvement over the baseline, it can be selected. For example, here common choice was PET, PPS, PA, PAN, and PCL. These were the common thermoplastic material that were used for this application. Again, this then among these five, the choice depends on the design requirement. For example, if there is a requirement of high G1, then one should go in this area, and if it is a high requirement for G2, probably go in this area, and if it's like somewhere in the middle, probably go in this area of the of these fracture toughness values. And similar for propagation energy. And from the perspective of areal density, one can ask, okay, one can pick one material. Then again, the question would be like, how much should be the areal density for this material? Then again, it depends on your design requirement, what kind of G1 or G2 improvement you are looking over the baseline laminate, and depending on this requirement, one can pick using these plots. And also areal density is moderately correlated with G2 and very low correlation with G1. Then about the toughening mechanisms, there are several toughening mechanisms introduced by this method of fracture, improving fracture toughness, starting with nanofiber breathing, because the fiber diameter is from about 200 to 500 nanometer, and it's randomly oriented, so it adds additional fiber breathing on top of the fiber breathing from the reinforcing fiber. Along with this fiber breathing, other toughening mechanisms are pullouts, plastic deformations, debonding, crack deflection, micro crack arrest, and so on. And all of these toughening mechanisms consumes a lot of energy and improves the fracture toughness, giving higher toughness value in the final laminate. So some experimental result on this direction. So as it is thermoplastic, it's not electrically conductive. So what we try to do was we add multi-wall carbon nanotube. And this was produced at Budapest University by our collaborators. And we try to make it conductive so that it can be used for self-diagnostic purpose. However, manufacturing of these polymeric veil, pan polymeric veil with multi-wall carbon nanotube was success, and but the desired conductivity that is needed for self-diagnostic purposes was not achieved. And the reason was that this multi-wall carbon nanotubes converts insulative into conductive when it forms percolation network in the material, and such percolation network was not formed, so this conductivity was not achieved. So to summarize this direction of research, interleaving polymeric veil is one of the effective methods for improving fracture toughness. Several material choices are available. A method based on achievable improvement in fracture toughness over the baseline is created for material selections. Toughening mechanisms are identified. Electrical conductivity of veil was not achieved. So self-diagnostic cannot be achieved using this technology. So we go to second method where this is interleave but produced from epoxy and CNT nanocomposite. So again, the problem statement is same, to improve the fracture toughness, but again, in addition to improving fracture toughness, we also want to have a self-diagnostic capabilities, and this capability can be used for damage monitoring, for structural health monitoring purposes. In this direction, there are several methods that already exist. For example, fiber modification, resin modification, interlaminar region modification, and pre-preg or fabric modification method. These methods are good and improve fracture toughness, but what are the problems? Some problems, let's go one by one. For example, fiber modification is in this method, the fibers are grown on the surface of the reinforcing fiber. Carbon nanotubes are grown on surface of reinforcing fiber, which is not scalable, because you can imagine a composite part, for example, aircraft wing, which is about several meters, and growing nanotubes on such big structure is not a scalable solution. Similarly, resin modification in this method, nanofillers like carbon nanotube or graphene is introduced in the matrix. But the problem with this method is that when you use this matrix dispersed with nanofillers, the problem like filtration arises. What does it mean? It means nanofillers in the resin are filtered by fibrous reinforcement, and also the viscosity of the resin is very, very high. So it creates a lot of trouble in impregnation, especially for vacuum infusion technology. Similarly, in interlaminar region modification method, in this method, the carbon nanotubes are aligned carbon nanotubes are grown in the interlaminar region, or it is grown on some substrate and then transferred to this interlaminar region. So what is the problem with this method? This method, the problem is that it is again not scalable, because again, this is the question of scale. How you can do a small sample in a lab for sure, but if you want to scale it to a real composite part, it could be really challenging. Similarly, another method is prepreg or fabric modification. In this method, CNT solution is used to coat the prepreg or fabric. What is the problem with this one? The problem is that usually the dry form of CNTs are chosen in this method, and handling such dry form is again has health related effects. So it has the problem of handling. So what do we propose in this direction of research? We propose interlaminar region modification method, and in this method, an additional layer is introduced in the laminate as an interleave. This interleave is produced from CNT master batch, and again, using the advantage of CNT master batch, here we can address these problems because it's additional layer, so no problem of filtration. And this master batch is now available at industrial scale, and so it is very scalable. It can be scaled to larger composite parts. And compared to dry form, it gives easier handling and good dispersion. And similarly, CNT interleaves is electrically conductive, so self-diagnostic is possible. So let's start the methodology of this research, starting with fabrication of composite laminate. These laminates were fabricated using compression molding of unidirectional glass fiber prepregs. Interleaves were produced by diluting carbon nanotubes. This diluting carbon nanotube master batch, and this master batch has single wall carbon nanotubes supplied by tubule. And here you can see the physical parameter of these carbon nanotubes, and this spec ratio is estimated based on this data of length and diameter. And the weight percentage in the master batch was about 10 weight%, and this is produced by 3-roll milling. So when these laminates are produced using compression molding, there is a problem of misaligned fiber, and this problem is solved by introducing a metallic frame. When we introduce this metallic frame in the compression molding, it restricts the flow, movement of fiber and within its frame. Similarly, since it is prepreg, we also need some gaps so that the extra resin is collected. The extra resin can be collected, and for this purpose, these gaps at the top of the frame was provided. This is the direction of fiber, so usually the fiber movement in this direction, in transverse direction, are larger, and this was controlled. However, the movement of extra resin was provided so that the extra resin could be removed. Regarding fabrication of interleaves, it's the process of diluting the CNT master batch. Two types of interleaves were produced, called LC interleave and HC interleave. LC interleave it stands for low concentration of carbon nanotube in the interleaves, and HC is for high concentration of CNTs in the interleave. The low concentration interleave contained about 0.6 weight% of CNTs, and HC contained about 7.5 weight%. Diluting master batch is a multi-step process, starting with step 1, where it's low speed mixing, then followed by some degassing step. And second step, it's a high speed mixing, shear mixing, followed by another degassing step. And then we add hardener, compatible hardener, and then mix again at low speed and degas before we introduce it in the laminate. Similarly, in compression molding, there will be some questions regarding manufacturing cycles and effect of temperature and pressures. Here you can see some results. 3 manufacturing cycles were chosen, namely A, B, C, and 3 temperature was considered, starting with 120 and ending with 160. And this manufacturing cycle was tested in DSC to see how degree of cure evolved during this manufacturing cycle. And it was found that when the temperature is set to 160, maximum temperature is set to 160, the degree of cure of about 99% was attained. Similarly, the effect of pressure also can be seen here, that when the pressure is about 5 bar, the fiber volume fraction of about 60% was attained. And this 60% is a requirement in aerospace industry. So this is kind of like a benchmark. When we are producing laminate, we always target to achieve at least 60%. Similarly, for lower pressure, what we observed was that there was some poor area in the laminates. For example, here you can see some air bubbles in the laminate, and also some poorly cured resin. And also this is verified from here. We can see that degree of cure for the temperature and lower pressures were only about 14 and about 60–70%. Some results, starting with dispersion of synth is, as it is the big question in multifunctional composites. So here you can see this is a SEM scan of master batch, and you can see some twist and turnings effects because this master batch was produced by 3-roll milling, which is a combination of at least 3 to 5 rolls. So there is this twisting effect in the master batch. And then when this is diluted in the interleaves, you can see this carbon nanotube in the interleaf is more or less dispersed, is more or less perfectly dispersed with few exceptional agglomerates. For example, in here, this region, some agglomerates we can see. So it doesn't matter how we mix it, still some of the agglomerates still exists. Characterizing the interleave in the laminate, the thickness of interleaves was between 200 to 250 micron, which is like thickness of 2 to 3 plies in the laminates. Introducing such interleaf decreases the volume fraction by about 7% in LC interleaves and about 3% in HC interleaf. And also in HC interleaf, here you can see we mix HC interleaf was diluted as master batch contains epoxy and carbon nanotube. So we need to add compatible hardener to this master batch. And once we add this compatible hardener, the weight percentage in the mixer reduces to about 7.7%, about 7.5%. And so to mix this mixer, I introduced some acetone, and this acetone was removed when interleave was transferred from mixer to the laminate. And because of this acetone, there is some effect on the thickness of the laminate. For example, even though LC interleave has thinner interleave, LC laminate has thinner interleaves, the thickness is about 3 millimeter. However, in SC, the thickness of interleave is about 31 micron, but thickness is about 2.88. It happened because there was acetone in this case, and this acetone it transferred because interleave itself is about 200 micron thickness. So even though the acetone from the top layer is evaporated, there is still some acetone at the bottom of this interleave, which is transferred to the neighboring ply layers, and this could have removed some of the extra resin from these plies, giving this lower thickness of the laminate. Some tests on characterizing the fracture toughness, starting with mode 1. This test was performed as per ASTM standard using double cantilever beam DCB test. Here you can see the setup of this test, and all three data reduction method was considered, namely modified beam theory, compliance calibration, and modified compliance calibration. And all these values was compared, and we observed that MBT method gives the most conservative value of G1, and it is in agreement with the ASTM standard requirements. So MBT method was used further for calculating G1 and for calculating and comparing G1s. Mode 1 toughness for baseline and modified laminates. The G1 value for baseline was about initiation energy was about 1000 joule per meter square, and which was reduced by about 80% in case of LC interleaf laminate. And also we observe a near constant R curve for LC interleaved laminates, and this is a weak R curve. However, in case of HC interleaved laminate, we see an improvement of 27% in G1 initiation, and propagation is about constant. Similarly, the R curve for these laminates is a very strong R curve and with a positive slope. So what is the reason for such improvement? We'll discuss just the next slide. Yes. So this can be answered from this toughening mechanism that we see from the SEM image of these fractured surfaces. Starting with baseline laminate, the toughening mechanism in these baseline laminates are fiber breezing. Fiber breezing between two plies in the interlaminar region, which give rise, which is the main toughening mechanism in the baseline laminate. Similarly, in case of LC interleaved laminate, we see some of the toughening mechanism. For example, tearing effects. This is supposed to improve fracture toughness. But what we observed was that before this tearing effects kicks in, the region where interleave and ply interacts, this debones. There was premature debonding at the interleave and ply region, which was the cause of such decrease of 80% in G1. Similarly, we also have some images from nanoscale. We can see some tearing effects, but again, this toughening mechanism, which was supposed to increase the G1, were masked by this microscale effects called premature debonding, and the overall fracture toughness decreased by about 80%. However, in case of HC interleaved laminate, here we have images from both microscale and nanoscale. So starting with microscale, we see some tearing effects, some tearing effects in the interleave, and also its tearing effect. It's 3D tearing effects. Okay, the picture is not here. Okay, anyway, and in the nanoscale, we see several nanoscale toughening mechanism. For example, CNT pullouts, CNT thinning, CNT breakage. For example, here we can see the CNT broke somewhere here, it's thinning effect, and also some nano breezing. For example, this CNT bundle, it kind of created, it teared and created this nano breezing effects. So lot of toughening mechanism at play at the nano scale, and also toughening mechanism at the micro scale. So it gives hierarchical toughening, that we have toughening mechanism at both scales, at micro scale, micrometer scale, and at nanometer scales. So it introduced a hierarchical toughening mechanism, which is the reason why we see improvement of about 27% in the G1 initiation energy. However, in propagation energy, this doesn't replicate. It could be because, when the crack is propagating, the crack sometimes deflects, and it goes to other regions, and the toughening mechanism could not act in such crack deviation, which could be the reason that we do not see similar effect on propagation energy. So how does this value compare to literature? Here you can see two plots. First, in its comparison in terms of percentage, change in G1 in terms of percentage and in absolute value. So in percentage, what we observe is that all four modification method, nanoscale modification method, has some detrimental effects and some positive effects. This was also in accordance with what we observed, because we also have a detrimental effect for LC interleaved laminate, and a positive improvement in case of HC interleaved. So 27% may sound like a small improvement, but it should be noted that this is a very high quality prepreg, as it can be understood from the baseline value of 1000 joules per meter square, which is very high value for G1. And you can see this developed 1D model, which is a resistance value that we measure from this set, from this test. in the DCB samples. However, in this model, there are several parameters. So for example, this resistivity, width, thickness, which may change depending on the interleave. So what I try to do is try to remove these parameters using the initial values. For example, at the initiation of the test, we know the length of the crack, and the resistance value can be measured using a simple multimeter, and we can use this value and we get this 1D model. This model is independent of resistivity, width, and thickness. However, here we have a LT, length of the crack. It's not exact length of the crack, but it's the effective length, because we consider here this model, and in this model we consider a halfway split, so which may not be representative all the time. So we redefine this L as not the crack length, but as the effective length of the crack of the arm. So using this model, we try to plot the data that we observed in experiment, and we see these two plots for LC interleaved and HC interleaved laminates. And we can also see these R values for LC was about 88%, and for HC was about 94%. So this small decrease in our R square value, it could be because this LT here, we consider it as an effective length. So self-diagnostic capabilities of these interleaves in the first figure, you can see it's for LC interleaves. And what we observe here is that both of these interleaves are electrically conductive because they form percolating network of CNTs. Both of these interleaves are highly sensitive to deformation, so this can be used for diagnostic and early damage detections. Regarding the phenomena in diagnostic characteristics, so there was no change or slight change in resistance until damage initiation, and there is a clear correlation between force, displacement, and resistance. So displacement here again correlates with the crack lengths. And here you can see for LC interleaved till the damage initiation, there is no change, and then we see a stepwise jump in the resistance value, which again correlates perfectly with the stepwise drop in the force during the DCB test. And for HC interleaved laminates, the initiation is somewhere here, and we see slight change in resistance till the initiation point, and then the resistance increases monotonically and the force decreases monotonically until the end of the test. So this is there is a clear correlation between force, displacement, and change in resistance. So these characteristics of these interleaved laminate can be used for self-diagnostic purposes. To summarize this direction of research, a method for interlaminar region modification for improving fracture toughness has been demonstrated. Self-diagnostic capability of interleave has been demonstrated, and this can be used for in situ damage sensing and monitoring purposes. CNT master batch is available at industrial scale, so this can be recommended for large composite structures. And the third functionality, it's on cure monitoring. So let's understand the problem statement. So composite materials are produce the main mechanism technology for productions are vacuum infusion, autoclave, and compression molding. In all of these three technology, it starts with the raw material and the intermediate steps like impregnation, stacking, and so on. And at the end, both the produced part is cured in the oven. When it is cured in the oven, the degree of cure of 90% or higher is desired for better mechanical performance of the composite structures. Here you can see this is a human standing inside an oven, so you can imagine the scale of such oven. This is from Airbus, I suppose. Yeah, this is from Airbus. And to monitor this curing degree of cure, there are several methods, starting with dielectric and ultrasonic, and also fiber optics. These are in situ methods, meaning it goes inside the oven along with your composite parts. There are also ex situ methods like NMR, FTIR, DSC. So these ex situ methods are also sampling methods, meaning these methods work when you have a sample from your structure to test. So this is a destructive method, mostly laboratory scale method. And also these dielectric, ultrasonic, and fiber optics are in situ method. However, they also have some disadvantages. For example, fiber optics is about the size of 150 micron. And you can compare this to the size of a reinforcing fiber in laminates, which is about 5 to 20 micron, depending on what fiber you choose. So you can see this mismatch between the diameter of optical fiber and reinforcing fiber, which could lead to potential damage site in future when it is loaded. So it compromises the property of the structure. Similarly, dielectric and ultrasonic, these are very expensive method and needs highly trained engineers and also expensive equipments to run such tests. So what do we propose? We propose to monitor QR status monitoring using a nano composite sensor. How would it work? Some schematic diagram of working mechanism. So this nano composite sensor will go inside oven with the composite part. So this is an in situ method. And then we just collect some data and do some data processing. And once we get the results that we desire, then we can control this curing process. So, and this is achieved because nanocomposites, conductivity of these such nanocomposites are very stable, so it's very easy to operate. CNT nanocomposites, the conductivity is achieved with very low percolation threshold of CNTs, so only a small amount of CNTs, so no added cost. Similarly, CNT percolation network, it changes with slight change in the viscosity or temperature of the base material. So this property was used in this study. We'll see the result and discuss more on this point again. And this change is because of the tunneling resistance change. So from this, we concluded that this CNT epoxy nanocomposite can be used to monitor curing process. So methodology, starting with the base material, which was epoxy here, tubule master base, same as that I used in previous research. This nanocomposite was prepared by shear mixing of master base with the epoxy, and then molding the diluted nanocomposites in the silicon molds. The characteristics of master base are here. And again, this mixing is more or less same process, starting with low RPM mixing, some degassing, followed by a high RPM mixing, and adding hardener, and which is followed by again low speed mixing, and final step of degassing before it is ready to be introduced in the composite laminate. This is the pictorial representation of what I just explained. Is some mixing step, and then schematic of this curing. This is the sensor in the oven, and here you can see the final cure sensor. So results when we measure electrical conductivity of these sensors, we see this typical pattern of a very big jump in the resistance. And then once it attains maximum temperature, there is a drop in the resistance, and then it attains a constant value. Just in a couple of slides, we'll discuss why this phenomena is observed. And during this curing, we also measure temperature inside the oven and try to replicate this same temperature time profile. It's also called curing cycle in the DSC to see how degree of cure evolve during such curing cycle. So to this data, piecewise linear fit was done to obtain this linear plot, the rate one. And this plot was fed in the DSC machine to see how degree of cure evolved during such curing cycle. So a little bit detail about DSC data. So here we have isothermal heat and total heat. This isothermal heat was measured during the DSC isothermal test, in which it's start with on-cure epoxy, and this on-cure epoxy is cured using this curing cycle that we obtained from the oven curing data. And the dynamic DSC test, it's needed to calculate the S total. And this was calculated from the cured sample, and to see if this cured sample needs any further curing, which means that this sample is still some small percentage still needs to be cured. And this heat goes in the total, and using these two tests, we can get this degree of cure evolution curve. So these nanocomposite sensors, here we saw that we have this jump in electrical conductivity with curing time, and we see degree of cure evolution with curing time. So these two data was considered, and we see that both of these data has a common variable called time. So we just remove this time variable and we get this plot. So it's degree electrical resistivity, or it could be conductivity, doesn't matter, against plotted with degree of cure. So here we can see a big jump around 90%. So it is a very good sensorial representation that once the degree of cure of 90% is achieved, we see a very good peak, and this could be indicative that the degree of cure of 90% is achieved, and based on this, we can control the curing process. So some of the characteristics of this sensor, it's nano-engineered sensor. It's a non-destructive method. It's in situ method. No need of costly equipments because we are just measuring electrical resistivity or electrical resistance. It's a continuous monitoring process, and it's easy to operate and very scalable. And also it gives the possibility to collect high frequency data and processing. And also we can use this technology for multiple locations, because some of the time when composite structure is very big, measuring this degree of cure at several locations is desired. And so this can be used for such application as well. So let's go into the detail of why we see this peak. So starting with mechanism of electrical conductivity. So the mechanism of electrical conductivity in such nanocomposites is explained by this CNT percolation network. It's a network formed by multiple CNTs in this polymer. Here you can see these CNTs form a network. However, these CNTs are not engaged in this percolating network. So at microscopic scale, we measure the resistivity, electrical resistivity, because it's a cubic sample, so we can reduce this to this simple algebraic expression. And then this R value is the sum of resistance of CNTs as well as tunneling resistance. So this tunneling resistance is the resistance at the contact point, because we know that any two material in this it doesn't touch each other at nanoscale. There is always some gap, and at these gaps, the conductivity happens by tunneling. It's a quantum phenomena, and this resistance is called tunneling resistance. So this tunneling resistance, it's a function of delta, and this is called tunneling distance. So tunneling distance is the gap between any two CNT or CNT contact. It could be end to end, like this one in A, or it could be surface to surface. For example, like one surface of CNTs to another surface of CNTs. This tunneling could happen here, and we need to know the tunneling resistance of such setup. Similarly, it could be end to surface contact, like this one. So one end of the CNTs is in contact with the surface of another CNTs in the percolating network. So I was talking about the minimum distance. So CNT is a carbon-based material. So for carbon material, van der Waals distance of carbon is about 3.5 Armstrong. So this is the minimum value of tunneling distance that can happen in the percolating network. So, regarding the mechanism, why this peaks is there when we increase temperature, and again why such drops. So it's explained by something called infiltration and shrinkage effect. So what is this? Let me go in detail of this one. So during phase 1 here, we see no change in resistance or very slight change, because there is no heating. It's just temperature is more or less is constant. It's at room temperature. However, at phase 2, the temperature increases monotonically and reaches to its maximum point. And during this increasing temperature, the viscosity of resin decreases. And because of this decrease in viscosity of resin, the resin infiltrates in between these CNT contacts. For example, at the initiation, at the phase A, let's suppose this delta 1 was the tunneling distance between these contacts. Then when this epoxy infiltrates, this tunneling distance increases and becomes delta 2, which is larger than delta 1. And again, it keeps on increasing until maximum temperature of this point, that is phase 3, is reached. So this will be the maximum tunneling distance in this whole process. And this coincides, this correlates with the measurement of the electrical resistivity. Similarly, after this maximum temperature and minimum viscosity point, the temperature becomes constant, so viscosity doesn't change. However, this is the minimum viscosity, so there is orientation of molecules, epoxy molecules, so it gives rise to another kind of conductivity from phase 3 to phase 4. Along with that, now this is the point when cross-linking happens. Cross-linking is that the epoxy molecules start to link with one another and it starts to cure. So it is known from the literature that data that when epoxy cures, its volume shrinks by up to 7%. So during this cure shrinkage and also the new conductivity because of the ionic movement during the initial phase of 3 and beginning phase of 4, this tunneling distance, it decreases because it's shrinking. So this tunneling distance in the percolating CNT network is decreasing. So what happens when this decreases is that the resistance, tunneling resistance decreases, and we can see such decrease in the overall resistivity of the nanocomposites. And at phase 5, when curing is completed, it reaches to some value delta V. Again, the minimum of this value could be the van der Waals distance, but it's difficult to know what exactly is this value. So this is how we explain this typical behavior of these nanocomposites based on the shrinkage, based on the infiltration at the beginning. When this infiltration happens, the distance increases, so resistance increases, and then the epoxy start to cure, and then it shrinks, and when it shrinks, the tunneling distance decreases and also resistance decreases. So we observe phenomena. To summarize this direction of research, electrical conductivity as functional property can be used to determine and monitor degree of cure. An in situ, low cost, efficient, scalable, easy to operate nano-engineered sensor has been developed and tested. Continuous monitoring of curing process advances quality control and productivity. To conclude my presentation, 3 functionalities applicable to multifunctional FRP composite has been studied. Polymeric electrospin polymeric veil shows hierarchical toughening, but self-diagnostic is not possible. Epoxy CNT interleaf has successfully shown both hierarchical toughening and self-diagnostic capabilities, so it can be used for structural health monitoring applications. Similarly, capability of epoxy CNT nanocomposite for cure monitoring has been demonstrated and can be used for quality control and productivity. These are some of the publications based on the thesis research, and 2 patents was also filed based on this research. Also presented at several conferences. And at the end, I would like to thank my individual doctoral committee, my collaborators, colleagues at Center of Material Technology at Skoltech, also KTO office, Skoltech History Grant, and all the jury members for considering me for review. Thank you.
Thank you very much, Biltu, for very comprehensive presentation. So now I request every jury member So if we could start probably from the audience from here, who is presenting here, first to ask the questions related to presentation and to the thesis, and then at the end, I would like you to state whether you are satisfied or not with the changes introduced in the thesis after the review, based on your comments, remarks, and questions. So if Dmitry Krasnikov, could you please start?
Okay, thank you, Biltu, for a nice presentation. And of course, as everything new, some questions arise. So, Elena, would you be so kind to bring back the presentation? So, the question is about slide 42, about the nice and comprehensive mechanism. So, I'm wondering about like the stage 3. So would you be so kind to explain once again what is happening during this stage and how long does it take?
How long does it take? Stage 3, it's so very difficult to answer. How long does it take? It's just like a moment when we reach maximum temperature. And at this maximum temperature, we have minimum viscosity of the matrix. So what happens is that before in stage 1 and especially in stage 2, the infiltration is happening in the percolation network, so which is increasing the tunneling distance. And in stage 3 is just a point where this maximum tunneling distance is reached. So regarding the time, I think it will be very instantaneous. It's very difficult to say what exact point of this time.
Okay, and the same question, sorry, the question is about the same slide. So the van der Waals distance between nanocarbons is over 34 nanometers, as you stated. But yeah, there is a force which holds them neither closer, neither to a higher distance. So what is like the driving force to the epoxy to go between those junctions? You know, because you need to like some external force in order to move carbon nanotubes.
Right. So here in phase 2, the driving force is temperature, right? And because of increasing temperature, viscosity is decreasing, right? So, and when viscosity decreases, it's very easy for resin to flow in channels compared to higher viscosity. So this change in temperature, which leads to change in viscosity, is the cause for such change.
So if we take epoxy without initiator, or like let's say some stable case of epoxy without further polymerization, and we just heat it with the system, it will also increase the
tunneling distance. Yes.
Okay, and maybe the last question, just out of curiosity, about slide number 2, if possible. So there were, what is like the difference between carbon nanoparticles and carbon nanospheres? Because like OD and 3D nanomaterials, so I'm wondering what's the difference between nanoparticles and nanospheres? Can you describe it?
Yes, not a chemist, but let me try to explain from mechanics side. So usually it's like 0-dimensional, and this is defined as less than 100 nanometer. So if it is less than 100 nanometer, we usually say this is nanoscale. If it is more than that, then we usually say it's microscale. So when we say 0D, it means all 3 dimension is less than 100 nanometer. Similarly, in 1D, at least one of the dimension is less than 100 nanometer, and we cannot say, and other 2 dimensional need not be less than 100, less than 100 nanometer. So 3D materials usually is like found by self-assembly, agglomeration of these 0D, 1D, and 2D materials. It could be either self-agglomeration of just 0D material, or it could be agglomeration or or assembly of multiple of them. So I think that should be the difference between nanosphere and nanoparticle.
So Thank you.
It's the dimension difference.
Have I got it correctly that nanospheres are larger than 100 nanometers?
Yes.
And how come then we define them as nanospheres? Because
I think it's just the popular term, like because every material wants to put nano. Just I think it's because of that. So if you talk technically, it shouldn't be a nanosphere. It should just be a sphere or the microsphere.
okay, maybe like now the really last one question
Yes.
about slide number 6. Also just out of so what kind of environmental factors could induce interlaminar stresses? Would you be so kind to
yes.
discuss?
For example, let's just take case of impact, right? So we see some visible damage on the top surface, right? And this is now open to air, water, I don't know, humidity, everything, right? So these environmental factors could trigger and accelerates the delamination. It's known in literature that environmental factors like humidity, environmental factors like moist air, these kind of things has effect on the usually on the bending property of the composite laminates. So this also has effects on the delamination.
Okay, thank you for the question. And like the last statement, I'm satisfied with the changes made in the thesis.
Yes, thank you very much, Dmitry. Now I would like to ask another Dmitry Klemensky, if you could tell so at the end also your statement and ask questions. Yeah, yes. First.
Well, actually, I have to pick on the same slide 42, please. Yes, so I have a few questions on this one. So first, well, you have cases. I think you call them A, B, and C. In the
Right.
slide, yeah?
Based on the type of contact,
Yeah.
A, B, and C.
So it looks like it's a planar configuration, is it? So it is impossible to have like this kind of configuration.
Yes, it's possible to be out of plane, but again, even if it is out of plane, if it is like this, it's end to end, or if it is like this, it's surface to surface.
Okay.
Yeah, because it's just like where you see it from, right? Once it is from one plane of view, it's like out of plane. But if you just rotate this plane of view, you will get only three kind of contacts are possible. Either it's end to end, or surface to surface, or surface to end.
Okay. Well, then next question: why does this matter for your description? Why do you need to introduce these cases A, B, and C? Or are they different in any respect? Well, I mean, geometrically they are different, but for your explanation, does it matter?
No, it's the idea was to consider all the cases, what could happen, right? So we do not know what is happening in percolation network because it's like at nano level, so we cannot see it. We do not know exactly. We do not have any pictures to see what is happening there. So the only idea is to see what are the possibilities. So these are the three kind of contact that is possible, and how these contacts could change to give such behavior. So this is why I consider all three of them.
Okay.
Yeah.
I see. Well, but then probably you answered my next question already. But let me just well, can you confirm that? So basically, this picture is just you're drawing from your imagination of what is happening. It's not
yes. Yes.
Okay.
It's the only thing that could happen. Because all this is three possible cases of contacts, and other cases I don't think.
So you do not have you do not have any image from any kind of experiment.
Right, that's right. Yeah, because it's at nanoscale. It's not possible to take such image.
Okay, then what I didn't really understand, you say that the as you heat it up, the viscosity becomes less, and then the material can flow in between these tubes. But what otherwise, do you have air, or do you have void, or what do you have if the resin can flow in?
Yeah, It could be anything. It could be a void,
Okay.
or it could be not air, because air is again maximum is nitrogen, right? So nitrogen van der Waals size is very big. It cannot go inside 3.4 Armstrong. It could be anything which is smaller than 3.4 Armstrong, or it's just a void, nothing.
Oh, okay.
Yeah.
I see.
Yes.
But then, at this small scale, can you actually
Probably it's a void. Yes.
talk about the flow if it's of the molecular size? Well, I was well. First, I was wondering, have you considered that it can be thermal expansion rather than?
Yes, I have considered as well thermal expansion. But you see this temperature, the temperature difference is about 100 degrees Celsius, right? So this temperature difference of 100 degrees Celsius from somewhere from.
From where?
Sorry, did I lose this? So here it's about somewhere around room temperature of 2730, yes. And maximum is about 130 degrees Celsius. So difference is about 100 degrees Celsius. Yeah. And the thermal expansion, as you know, is like very less in 10 power minus 6. And when you multiply this with 100, it gives very small change, maybe less than, I don't know, 0.1%. So it's very minimum. If it was a temperature difference of, I don't know, maybe like 3 order or 4th order of temperature difference, probably that would be one of the primary mechanisms.
But small in comparison with what?
With infiltration effect, the effect of viscosity, because viscosity it changes a lot.
How do you know that it's viscosity? This I don't understand. I mean, it can flow out. I mean, you can make the same argument saying that okay, the temperature goes up, so it can flow out.
Flow out of.
Well, out. I think somewhere else.
Yeah, we considered temperature actually, and we did some rough calculations, and we concluded that this temperature difference of 100 degrees Celsius was not, it won't give big change in the length of this length. Again, here correlates with tunneling distance, right? And this change in 100 degrees Celsius is not enough to give such big change in the tunneling distance.
Okay, so how large is the tunneling distance, you say?
Usually, so the minimum is 3.4 Armstrong, and it can be anything larger than that.
Okay, 3.4, and the thermal expansion distance?
It's so you can just imagine the thermal expansion is usually 10 power minus 6, and you just multiply this with temperature difference of 100. So it's 10 power minus 4.
So 10 power minus 6 per 100,
10 power
100
minus
degree?
4 for 100 degree temperature difference.
So it's like 0.1 millimeter.
0.1 millimeter. Then again, you have to multiply this by the original distance of 3.4 Armstrong.
Why?
Because you're measuring the change in the distance, right? You're not measuring absolute value, but change in the.
Okay.
Yeah.
Well, anyway, so I probably should stop here with this. Well, maybe slide 38 if you can.
Slide 8.
Okay, 38.
38.
Yeah, 38. Okay, so here you put, well, in the figure in the middle, you put the raw data and the process data. And the raw data has heat flow, what? Negative in the end. And the process data has heat flow 0 in the end.
Yeah, only at the end, because.
So what is this kind of processing? Or maybe you can comment on.
Right. So so only processing that what we apply here is that it was to establish the baseline actually, so that when you do this integration, this curve is becoming smooth. That's all. There was no other purpose. So to establish the baseline, and then once we have this baseline, we integrate it to get this smooth curve. Otherwise, it will be not too smooth. It will be very rough. And the most important one here in this experiment, I would say, is this test, because of course this test, and along with this test as well, because in this test you can measure if the cure part need any further curing. For example, what I understand from literature is that you can never cure to 100%. There's always like 1 or less than 1%, which can never be achieved. It's just like cross-linking reactions. So always there will be some finite value here. So this gives like this gives the understanding that degree of cure will never be 100%. It will be always a small percentage less than 100%. And regarding data processing, it was only to establish the baseline to get the smooth curve.
Oh, okay, good. Well, I think that's all. Just I was curious about these things, but otherwise I'm satisfied with the revised thesis.
Okay, thank you very much, Dmitry. So now we are going to the jury members who is present in Zoom. So and first, I would like to ask Professor Amit Raval to ask questions and give your opinion made on in the thesis based on your comments.
Okay, thank you very much, Mr. Chairperson. Mr. Biltu, I think you've done a fantastic job. Thank you very much for your nice presentation. One of the things that I like most about is the negative results that you have presented in your thesis, which is rarely shown in any work. So this counts a lot, actually. Thank you very much for that. Okay, I have few questions. I don't mind if you don't mind answering them. Especially they are coming from your thesis. So I've gone through the thesis again with the necessary changes that you made. So for our first question is, you claim that the diameter of the nanofibers in the veil varied from 200 to 500 nanometers, whereas they appear to be very uniform. And secondly, you said it's a random orientation of fibers, but there was a figure 2.8 that had a preferential orientation. Most of the fibers appears to be aligned in one particular direction. So do you think you have made the correct statements there, or do you want to correct them again?
Elena, can I have presentation? Elena, can I have presentation? I don't remember the number. Let me just.
It was in your thesis, actually, in the revised.
Yes. Yeah, I have it here as well. Just maybe a couple of FCM pictures. Yes, here. Yes, Professor Raval, if you see this image here at the corner, so can you share? Yes. Yes, if you see this picture at the corner, so here this SEM image is taken for a bigger area, right? So here you can see this is not oriented. It's just look oriented because this image is for a very small area.
No. Please, you have to go into your revised version of the thesis, and there you can clearly see in figure 2.8, there is a preferential orientation. Some of the fibers are aligned in one particular direction. But in any case, even if you say it's a random orientation, how do you make the justification?
Right. So I think it looks oriented in image. It's because this image was taken for a very small area, right? And even if when you take SEM for a very small area in random orientation in a very small area, it looks like it's oriented towards some direction. So I think it is just the perspective of view, and because of a small area, it looks like oriented. But this is randomly oriented. No, usually orientation in electrospinning, it's achieved by applying some electric field or some magnetic field. But in this case, we did not apply any electric field for orientation. Of course, there was a field for the electrospinning, but no electric field for orientation when it is collected at the drum, right?
Okay. Let me just give you the correct answer. You meant to say that if there was a roller rotating and you actually make the fibers onto them and they're rotating at a higher speed, then you will get the preferential orientation. Otherwise, it's a nearly random orientation. I believe
Right,
that's
that could be one way. Yes, yes, that could be one way. And also in the drum, rotating drum, also you can put some additional field, either magnetic or electric field. And if it is, and then sometimes such interaction can happen when you can make highly oriented one. Recently, when I was in one of the conference, I saw one presentation from, I don't remember exactly, but their goal was to make it highly oriented, and that is how they did it. And it's also widely reported in literature as well.
Okay, coming to the
Usually
second
electric
point.
spinning is randomly oriented.
Yeah, coming to the second point that I raised here, these fibers appear to be very uniform. And now you don't, I mean, how do you justify it's a large variation of 200 to 500 nanometers? It appears to be very uniform structure. Perhaps you should revisit your results. That's what I can say.
So
Right?
yeah, regarding the diameter, it's, I think, average of not from only one SEM image, but from several images. And because the manufacturing condition was kept constant for all cases, starting with 0.5 weight percentage of multi-wall carbon nanotube to 5 weight percentage. So this manufacturing condition was same, same potential, same distance, same environmental conditions.
That's fine. Absolutely.
Yes.
Mr. Biltu, but you know, whatever you have to give the justification with evidence. So if you say that you have a fiber diameter of 200 nanometers, you show me some images on that front, and if you show that there's a large variation up to 500 nanometers, then you should give a scientific evidence, because now since you are showing one image here, now you're claiming there's a random orientation and is obviously between 200 to 500 nanometers. It's difficult to justify because some of the things that you showed in the thesis was a little different. That's the reason I had this confusion. I'll move to the next question if you don't mind, right?
Sure. Yeah.
Okay. In case of LC interleaved laminate, obviously I saw that there was an increase in the resistance, and the change in the resistance followed your tensile behavior, which is quite nice. But how do you correlate your results with the mechanics of the electrospun materials? Because I remember Professor Steven, when I was there at KU Leuven, he once mentioned in one of the defenses that nanotubes are the eighth wonder of the world, or the nanomaterials are the eighth wonder. Since these materials are embedded within the fibers, how do you justify that they are able to, or sense the damage or sense the change in the resistance? How do you say so? And how do you relate with the mechanics of the electrospun materials?
Elena, I just lost. It's not working.
Can you hear me?
Yes, yes. Just give me a moment. I'm trying to put the slide and then I will try to answer your question. Yes, okay, it's working. Yes. So here you see for this, this picture is just a larger view of this picture. So here we see this correlation between change in resistance with change in force, right? And here displacement, but this displacement is correlated with crack length, right? So you can use this dependence. Look, for example, with increasing displacement, you see change in resistance and also change in force. So you can use this as a sensorial data to develop this damage monitoring sensor. Similarly, in case of HC interleave laminate, this dependence between change in resistance to change in force and displacements. Again, this displacement is displacement of the fixer, but this displacement is correlated with the crack length. So once you have this dependence of crack length, displacement, change in resistance and force, I think this you can use as a sensorial data to monitor damage.
But how do you correlate with the mechanics of electrospun materials? Let's say, because it's a veil which is made up of nanofibers, and obviously when you try to stretch them, obviously what's happening, and how do you correlate the change in resistance? What is actually happening to the material itself? So that's what my question was.
Right. I think you're talking about polymeric electrospin
Yes.
veil, right?
Yeah.
So yeah. For polymeric veil, we do not see any self-diagnostic capabilities. This self-diagnostic capabilities was only visible in epoxy CNT interleaves.
Okay.
Yes,
Okay.
yeah. For polymeric veil, we didn't observe any self-diagnostic, only toughening effects.
Okay. Okay. And please describe hierarchical toughening for me. It was not clear. If you can kindly.
Right. So how I define so hierarchical toughening is usually like when you have toughening effects as two different or at multiple scales. For example, here in my case, I see toughening mechanism at nanometer scale. So toughening mechanisms like CNT pullout, CNT thinning, and breakage, and also toughening mechanism at micrometer scale. For example, here tearing effects. This is like tearing of CNT. So tearing of CNT interleave. So this consumes energy and improves fracture toughness, which is at micro scale. And then we see toughening mechanism at nano scale. So we see toughening mechanism at multiple scales. So such toughening is called hierarchical toughening.
Yeah, but then this is the only case with higher amount of CNTs, right?
Right.
With the lower amount of CNTs, that was not the case.
Right. Yes.
Right. But then you have generalized your conclusions. If you look at the slide number, I don't know whether it was 44 or something, which was a conclusion slide. Yeah. So you see point number 2. So electrospun shows hierarchical toughening, but that is the only case when you have higher amount of carbon nanotubes.
Right.
Not with a lower amount.
That is correct.
Right.
This should be corrected. Yes, I agree.
Okay. Yeah. So and if you keep on increasing the amount of CNTs that what you proposed, let's say 7.5%, you still believe that the hierarchical toughness would be the hypothesis of in this case, or do you think something else will change?
Actually, if you keep on increasing this amount of CNTs in the interleaf, again, it depends because at higher weight percentage of CNTs, the problems like dispersion, the problems like agglomeration, the problems like re-agglomeration will come, right? So it depends on how we'll address these problems. So if you can address agglomeration problem properly, or the better version would be like you just put aligned CNT, right? I think there was one image. Let me put. Yes, you can see here. For example, in fiber modification, that is totally very highly aligned CNTs. And similarly, also in this paper from Garcia, they did with very highly aligned CNTs. And yeah, if you reach like such alignment at such higher percentage, then maybe you have a better fracture toughness. But achieving such alignment at such higher percentage would be very difficult. So I think it depends how your CNTs come into your laminates, and depending on this, the toughening either it's improvement or reduction. It depends on how it is present in the laminate.
Okay, and you mentioned, I think you measured the thickness of the electrospun material as well, right?
Thickness, I think no, I didn't measure the thickness.
Okay.
Yeah, it was only areal density and conductivity. Two tests was done. So areal density, it was more or less constant because same manufacturing conditions. And conductivity, we couldn't measure even at a very high percentage of carbon nanotubes.
Okay, a general question is, what are the factors that influence the percolation threshold of any conductive network? What are the factors you feel that they are the most important ones that influence the percolation threshold?
Yeah, so I think first of all, it depends on the nanofiller. For example, if it is CNTs, then the factor could be aspect ratio, right? And if you have larger CNTs, then your network can be found easily. Another factor could be the base material. For example, if it is thermoplastic, which is very viscous compared to highly viscous compared to thermosets, probably this viscosity has also effect there, because it's very difficult to disperse carbon nanotube in high viscous material. Another thing could be also the manufacturing method that you use. For example, if it is 3-roll milling, the dispersion is much easier, and when you have highly dispersed, the network can form at very low weight percentage. But when it is not dispersed, even adding very high weight percentage of CNTs can give you no percolating network. So I think it depends on multiple factors, starting with base materials to the geometrical parameter of the nanofilers.
Okay, so I believe what you try to say is the aspect ratio, which is important in your case. But I also believe the alignment of the nanotubes or the nanomaterials is also important.
Yes, alignment also, of course, yes.
Yeah. So in your case, you have taken 0.75%, right, of CNTs, and at what first level and the higher level was 7.5%?
Yes.
Right?
Yes, that is correct. 0.6 and 7.5.
0.6 and 7.5. It's a large difference. How do you justify that? That when you have 6.5% and the aspect ratio is more than 2000, and then obviously for developing the percolating network, you need very small amount, isn't it?
Right. That's correct. So yeah, so the idea behind 0.6 was exactly the same idea what you just told, because for percolating network, you don't need very big amount, especially when you have such higher aspect ratio. It's can be achieved as very low weight percentage. So the idea of choosing 0.6 was to keep it low and make it easy for dispersing this low weight percentage of CNTs. So the idea behind 7.5 is that the master batch that we use in this research has 10 weight percentage. And this master batch contains carbon nanotube and epoxy. So we need to add compatible hardener in this master batch so that it can solidify and form structured material, right? So when we add hardener to this master batch at 10 weight percentage, the weight percentage in the overall final mixture that we get, it decreases, right? From 10 to somewhere about 7.5%. So what I did was I just adjusted this value. I think it should be, this value to get exactly 7.5%.
Okay, are there any positive results of lower amount of concentration of CNTs in your project or in your PhD topic?
Could you repeat? I didn't get this.
So what I'm trying to ask you is, in case of LC interleave, let's say, which has lower concentration of CNTs, are there any positive results that you observed in your work?
Yeah, for toughening effects, no positive result. It was only reduction in fracture toughness. But for curing, 0.6% was enough to show this curing, shows this property that can be used as cure monitoring sensor.
Yeah, because I think there you showed how the change in resistance followed the similar behavior, the tensile behavior, right? If I understand correctly.
Right.
Last question. You have shown a very nice work, but where do you see its future? What is the scope of taking this work to the next level?
Mm-hmm. So in the toughening direction, I think now, since we have established that at 7.5% there is good improvement in fracture toughness, I think the next direction, future direction in this direction of toughening effect could be to study the mode 2 effect and also mixed mode effect, because fracture toughness, it's characterized in 3 different modes. Here I only studied mode 1, which is the most important mode as quoted in a lot of literature. But again, I think mode 2 also should be studied to get the complete picture of this toughening effect. Similarly, in the curing direction, I think the next in the future direction in that research could be towards establishing this curing effect with complicated parts, complicated composite parts, which has, you know, like curved part, maybe some twisted, some bending, right, which has very critical part when it is cured in the oven. So we can, I think next direction in future could be to use these sensor in such complicated composite part and see if it works there as well and how good it works.
Thank you very much, Mr. Biltu. Mr. Chairperson, I'm very much satisfied with the response of the candidate. No more changes are required. Thank you very much.
Thank you, Professor.
Thank you very much. And so we have the last, but not least, jury member is Professor Kyung Liu.
Yes, please. Thank you, Chair. Hi, viewers. Thanks very much for your nice presentation. I have two questions. The first one is about the toughening mechanism in chapter 3. Can you go to slide, I guess, 27? Yeah, yes. In your factory analysis, it seems that it can very easily to find the toughening mechanism related to CNTs. And in your experimental data, I see it has very significant enhancement on the initial fracture toughness, but it has almost has no effect on the propagated fracture toughness. Have you considered why?
Could you repeat? I didn't get the last part. Effect of what you said?
I mean, in last night, you have observed a very significant toughening mechanism related to CNTs, right?
Mm-hmm. Right.
And yes, and also you found that when you induce CNTs, the initial fracture toughness has been increased significantly, but the propagated fracture toughness, I mean, there is almost no effect because you observe 0.5% increasement.
Right.
So, I mean, why? Why this toughening CNT-related toughening mechanisms has no effect for the propagated fracture toughness?
Right. So I think it is because of the crack deflection. So, you know, when in a test like DCB, it's very common that crack deflects from the interlaminar region to the neighboring region where it's the region of interaction of ply with the interleaf. So when such crack deflection happens, it's just underestimates the fracture energy. Also, you can, I think, just give me a moment. Yes, here. If you see these plots on the left, the R curve, at the beginning, you see for HC interleaf, the propagation is higher than the baseline. And it only decreases after somewhere in the middle of the test. I think it is because the crack was deflected from its initial path, and this gives lower estimate of the G1 propagation, and because of this the overall average also decreases. I think it's because the crack changes its path.
Okay. Can I also go to slide 26, I guess?
Slide you see?
26? I remember you have oh, no. Maybe a previous one. Before, I guess maybe 25, somewhere. You have two SCM pictures. It shows the laminate structure of the baseline and HC interleaved laminates. It shows that for HC interleaved laminates, the interlayer thickness is larger than the baseline composite, right? But the oral thickness, yeah, that's one.
Right.
Yeah, but the total thickness of the laminates, the HC interleaved laminates is smaller than the baseline, right? I say Yeah, in the table below.
Right.
I'm curious, where do you think the limit structure, does it have any effect on the experimental results? Because I also remember in your thesis, you mentioned that for the HC interleaved laminates, the thickness is unsymmetric. Because the fractal are calculated according to some theoretical equations. I'm not sure whether it's also is still valid for in this case.
So yeah, let me try to answer one by one. So here, yes, here we have the expressions. We can see the thickness is only considered in MCC method. But in my research, I used MBT. What happens lost now? So I use MBT method, and in MBT method, there is no consideration of thickness. So this value, whatever we measure using G1, it doesn't depend on thickness. And second question about this difference in thickness. So first, let's start with interleave thickness. So interleave thickness for LC is about 206 micron, and for SC is 231 micron. So how do I explain this? This is because in SC interleave there is a higher amount of CNTs and it's CNT interaction. So compressing this higher amount of CNT is difficult. And for both of these cases, the applied pressure was 5 bar. So it's, I think, because of higher concentration of CNTs in SC interleave, the thickness is larger than the thickness in case of LC. Similarly, when we go to the thickness of the overall laminates, we can see that even with the even with the thicker interleave, the overall thickness is just slightly larger than the baseline. So this can be explained by the constituents of this SC interleave. So if we see here, what we see is here that in SC interleave we have acetone. Maybe this figure would be better, but I don't know how to take this out. So yeah, so the point was that in SC interleave we have acetone, right? And this interleave is about 200 micron, and when this interleave was introduced on the laminate, it was left for about 3 to 4 hours to evaporate this acetone, because acetone, it can just evaporate at the room temperature. Yes, I think it's here, somewhere here. Yes, acetone we have about 20 grams. So this is 231 micron. It's quite thick, and the acetone at the top surface of this interleave is easily evaporated. However, the acetone at the bottom of this interleave thickness layer, it's possible that all of the acetone didn't evaporate there, and it transferred to the plies that is adjacent to this interleave layer, right? And because of this transfer of acetone from the bottom of this interleave, it's possible that some of the epoxy that was in the bottom ply layer was washed out, and so this extra epoxy was washed out, and because of this washing out effect, we see that the thickness of this SC interleave is just only slightly higher than the baseline thickness. I think that is how we explained our results. And it makes sense because interleave itself is about 231 micron, and evaporation at top is very easy and done, but at the bottom maybe it was not evaporated completely.
Okay, another question. In the future, if it's possible for you, to make the interface thickness is thinner, for example, maybe decreasing the content of CNT, maybe you can obtain CNT interleaved laminates with relatively small interface thickness. Is it possible to achieve the improvement for both initial and propagated fracture toughness? Do you think it's possible?
Yes, it could be a good research topic to control the interlaminar thickness, interleave thickness, and see how it could affect the fracture energy, right? So I think, yeah, it's possible. So we can probably, control the amount of acetone, or probably control the pressure applied, and based on this, or maybe it could be some other factor as well. So considering these as like input parameters, maybe we can, optimize this thickness. It's of course a very good research question.
Thank you. The last question is for the for two slide 42 as well. Sorry.
You said slide 24?
42, sorry.
So, 42.
For the current monitoring.
Right.
Yeah. Have you tried only, one cent content to obtain the result? The sensitivity of the electrical resistivity variation with the current degree. Here you I forget the content of the cent content, and that's the experiment result. So have you just tried one? Is optimum cent content to achieve very significant sensitivity of the electric resistant variation with the current degree?
I didn't get the question. Could you ask the question again?
Have you tried other cent content, or have you studied the effects of cent content on the variation of electric resistance with the current degree?
Yes, it's here, I suppose. Yes, here. So resistivity with degree of cure, this is the plot. And yes, this is obtained by just...
No. For different cent content.
Difference in content, you mean?
Yeah.
Yes, so regarding the content...
Do you understand? Because I think maybe the average distance between centers is very important for your current monitorings.
You mean effect of CNTs on the curing?
Yeah.
Okay. So yeah, I think I got the question now. Thank you for this question. So what regarding the effect of CNTs on the curing, what we found from literature was when the weight percentage of CNTs is lower, like this case, for example, 0.6, there is no effect on curing. But if we go to very high percentage of CNTs, like in literature, what we found was when the CNT weight percentage goes above 10%, there is some effect on the curing, usually with the heat dissipation, because CNTs are also thermally conductive. So they dissipate some heats, and it has some effect only at very high weight percentage of CNTs. At lower weight percentage, there was no effect.
Okay. Have you done such experiments?
Not really. We have not done this experiment, but this was studied by other groups, and this is well reported and well understood.
Okay, that's my question. Thank you very much.
Thank you.
Okay, and so what's your statement? Are you satisfied with the changes in the thesis? Professor Liu?
Yes.
Okay. Very quick and understandable. So, and I am the last one, so who could ask, but basically all the questions have been raised already and carefully answered. And I have only one, then a very simple one. So if you could open to the slide number 14, please. So as was already mentioned by Professor Raval, so you have demonstrated, you have shown some negative results, so it's good, of course. So, but I have a question related to these negative results. Now, you already almost a PhD, very close to this position. So when you did these experiments, so you were just only in the beginning. I understand you could make mistakes, errors. So if you were now at the position starting those experiments? What did you change? So what kind of advices you would give to you when you were in the beginning?
Regarding experiment, you mean?
Yes, so that the negative result will be positive here.
Well, if you talk just for this case, negative and positive result, I think no advice, because I'm constantly following this topic because I'm very interested in this one, and there is no positive result reported yet, even after 4 years. So the recent development in this field is people are now trying to electrospin conductive polymer itself. There are some polymers which are conductive, not so conductive, like somewhere just above the semi-conductive range. So people are shifting towards this instead of focusing on nanofillers. So I think because if there was some mistake in experiment, at least some of the groups would have come up with these results.
Yeah.
And I have not found any such result yet. So I think no.
Yeah, but how about, so you did it only up to 5%. At some
Right.
point it must percolate, right? So
Yes. Theoretically, yes, I agree. It should percolate, but it's very difficult to digest that. When we began this test, that was our thinking, like 5% is already too big of a percentage to get this percolating network. But I think it depends on the base material, right? But here we have this thermoplastics, which viscosity is very, very high, and again, this dispersion and all those problems are there. So I think this could be the thing.
okay, then, so I don't have any more questions, and also I need to say that I'm satisfied with all changes which you introduced in the thesis. And now we are going to the questions from the audience in Zoom, right? Are there any questions, Elena?
At the moment, I can see none. Maybe we shall make one more call for questions. Or...
Yeah, so if anyone in Zoom would like to ask a question, could you raise a hand or write it in the chat? So you still have a couple of minutes for that. Meanwhile, so probably we could switch to the word of supervisors. Yes, so Professor Sergey Baimov, so could you please tell your
Dear colleagues, good day. First of all, I want to thank you all committee members, first of all, becoming committee members, and for all help and corrections proposed to the research. Coming to Biltu performance, I think his work was outstanding and exemplary. So we worked with Biltu for 6 years. I was his master advisor at master studies. He published his first paper at the end of his master studies in high-ranking journal. And now you have, what, 15, right? And now, by the defense, he has 15 papers, very high-ranking journals, for example, Composite Science of Technology, one of the top journals. He has successfully secured 2 patents, 2 patent applications, including a Chinese one, already submitted, and very soon we will submit the 3rd one, right? And besides that, he also, for example, besides material of the thesis, he participated in international benchmark on permeability, publishing his results only virtual permeability, publishing his result also in a very high-ranking journal. So I consider his work as exemplary, outstanding, and I think this is one of the best defenses in Skoltech. Thank you.
Thank you very much. And if I could request Professor Stepan Lomoso to express your feeling about the candidate.
Yes, do you hear me?
Yes, we can.
Yes, fine. I second opinion of Sergey about work of Biltu. One thing which I would like to probably to add is that the work which we have seen today is very diverse, I would put. It is combined of many different directions, or several different directions of putting interleaves. And I'm very grateful to Professor Raval for his comment on negative results, which we decided to include, or Biltu decided to include with our support into this, because these negative results not published, but they are important to have and to show somewhere accessible. Another aspect of this work is that the work of Biltu was done in collaboration with many people, including people which probably are not that visible in the presentation, which is people in Hungary, in Budapest, with whom Biltu collaborated in producing this nanowhales, or who produced nanowhales. And second, this is unseen collaboration with MIT, unseen in the thesis, but which happened in reality, is unseen in the thesis just because of aspects which are not scientific and which refer to political situation. But the collaboration was there. It is referenced in Biltu's thesis. This is also an important aspect. So I think that this is a good thesis and fully deserved the degree which Biltu seeks.
Thank you very much, Professor Lomov. And so now is the time for closed deliberation. So I request everyone from the audience leave here only jury members for the discussion. And for those who are in Zoom, so we will invite you to breakout room for the discussion for the student candidate. So we had a long discussion, but everybody gave pretty much the same comment, that the thesis is ready, the candidate is ready to become a PhD. And so all 5 members voted that the thesis is accepted as is. So there, Biltu, congratulations.
Thank you.
So if you would like to say something, so it's time to do this.
It was quite an experience. Always wanted to have PhD, finally had it. Thank you everyone. And a special thanks to Professor Nasibulin, Professor Krasnikov, Professor Kolomensky, Professor Rowell, Professor Liu, and also special thanks to my advisor, Professor Obaimov and Professor Lomov, and big thanks to Professor Lomov for answering all my stupid questions. And also thanks to my colleagues from my lab. And yeah, thank you everyone. Finally, I'm a PhD.